Hi everyone, and welcome to the section 3.1 video. So we've made it to the point where we now get to learn some shortcut rules for doing derivatives. And this is the point in the class where it just becomes kind of a grind of memorizing the rules, practicing them, and trying to pick up on patterns and build some intuition for when you should use what rules, what functions you've taken derivatives of that are similar to others so that you think you should apply a similar rule, that kind of thing. But that really all comes with tons of practice, which is what you need to do. So let's get into the rules. The first rule here is the derivative of a constant function is 0. If I have a function f of x equals some constant c, so let's just pretend it's 3. Always do an example. So then, just quickly, what am I saying here? 1, 2, 3, here's my function. Okay, well, that's clearly not a very good straight line, but just think of it as a straight line. What's the derivative supposed to be doing? It's supposed to be telling you how this function's changing. Well, the function's never changing, so then the derivative is 0, right? There's never change. No change in the y value. Doesn't matter where I go in x, there's never any change in this y value. Done. That's it. But it's important to think a little bit about it, right? So, okay, not too bad. Next rule. This is the power rule, and this is the rule you're probably going to use the most out of any of them. So this has to do with powers of x. Now, a lot of the powers. So to start, we'll go with n as a positive integer. But we're actually going to expand this to many more things. But just when you start off, you can deal with things like x squared, x cubed, x to the 4th. Might as well just put x in there, etc. Okay, so what's the rule then? Well, here's the rule. You take your function. Let's just do an example as we're doing this. X squared. Do the derivative. You take this number, drop it in front. Okay, so the exponent gets dropped in front, 2, and then you take that 2 minus 1, which is 2x. So what's happening here? The power drops by 1, and you multiply by that original power in front. That's it. So do some more examples for yourself. Just try some stuff. X to the 7th. Drop the 7, x to the 7 minus 1 is 6. Keep going. Whoops, d over dx. What am I doing? So we've got d over dx here of x to the 15th. Doesn't matter. 15x to the 14th. So this is just something that is going to become quick. Quick. You're going to be doing this. You're going to be seeing this a lot, and then you're just going to be kind of powering through these. Right? This can be extended, though, past positive integers to many other numbers. So we can extend this past the positive integers. So let me give you an example. Let's let our function f of x be, so let's extend this. Let's let this be x to the negative 2, which is really just 1 over x squared. Now, if you see this, and you'll see this a lot, we can rewrite it algebraically in this form. This is key, really important idea going forward. You're going to run across problems where you're going to see this, knowing this rule. You're going to see this and be like, okay, this is a new one, I don't know what to do. But you do have the rule to do it. You do know what to do. You just have to make this algebraic step, right? So if you see x to a power, even if it's on the bottom, just move it up by putting a negative here and deal with it using the rule. So what's the rule? Drop the negative 2, subtract 1. Done. It still works. The rule still works. So you could try that with a bunch of numbers. You could try it with fractions. Let's go with a fraction. So let's say we have x to the 3/2. Okay, what's the derivative? And you'll notice I'm mixing up notation here, right? So I was using d dx over there. I'm using f primes here. We got to be comfortable with all of it. Drop it. Subtract 1. 3/2 minus 1 is 1/2. Boom. So there you go. Power rule. If you have x to a power, it doesn't matter what the power is, x to a power, you drop down the power, multiply in front, subtract 1, you're all done. We're going to come back to this one in another rule or two. Okay, constant multiple rule. This is a really useful one. This is useful because you're going to run across a lot of problems that look more complicated, but in reality aren't. They're just a combination of simple things. So for example, if I have the function 3x squared, and I'm say do the derivative, well, you should look at this, and before the constant multiple rule, you should say, I don't have a rule for this. True, but we have the constant multiple rule now, which says this 3, I don't care about this right now. Get it out of here. And what does that look like? And this notation is better to see what's happening. And hopefully when you see this happen, you go, oh yeah, I remember this from the limits. We can take the 3 and pull it out of the derivative, just like we could pull a constant out of the limit. So this is really equal to 3 times the derivative of x squared, which we know that, right? We have the rule, 3 times drop the 2, x to the 1, because I do 2 minus 1, which is 6x. All done. There you go. Constant multiple rule. If you have a number multiplied in front, you can just move it out of the derivative. It doesn't go away, right? It's still there, but you can move it out. And you could think about, you could think about this. So just compare this example, right? Compare these two functions. What's the derivative supposed to be doing? It's supposed to be telling you how fast you're changing. So, okay, if I know f prime here, how fast I'm changing for every x, then what's the difference between this function? Well, this function is just multiplied by 3. So shouldn't the rate of change just be 3 times? If this is f of x, shouldn't the rate of change just be 3 times the rate of change of this one? All I'm changing here is times 3. So the speed of the particle, the whatever you want to think of, should just be tripled. That's it. That's what this rule says. Okay, so pull out the constant. All right, the sum rule. Oof, this is a big one, very important one. If you have two differentiable functions, this should remind you of the limit rule, right? If you had two limits that existed individually, right, then when you see a sum of two functions, you could just do the derivative of each. What's the way this is going to come up the most? Not always, but the most is 3x cubed plus 4x squared plus 3. This is my function. Okay, how do I do the derivative of this? Because again, if I'm just sitting there like derivative of all this, you should say rightly, I don't have a rule for this. Give me any individual one of these and I gotcha. But I don't have a rule for addition. I do now. The sum rule says what you can do is you can do each of these individually. So let's do it out and use all of our rules. 3x cubed plus the derivative 4x squared plus the derivative 3 of 3. Okay, constant rule, constant multiple rule, constant multiple rule. And then here, the derivative of just a constant is 0. Okay, this is our power rule. So drop the 3. That'd be 9x squared. Don't forget, subtract 1. Okay, drop the 2 plus 8x. Subtract 1, you get 1 up here, which we usually leave off. And then 0 is 0. Boom. So that actually means that if you ever give me any polynomial, I know how to do the derivative now, because it's just a bunch of power rules added together. All right, not too bad. So the sum rule, very important. Just do them piece by piece. Okay, so there actually is another rule in the book called the subtraction rule, but come on now. Subtraction rule, it's just the same as the sum rule. Just do them separately. Don't forget the minus sign. So you see an addition rule, there's probably a subtraction rule right behind it. So this works for subtraction too. I will make a comment on, and like just do an example with the subtraction and just kind of show you the ways you can think about this, which can be useful in some instances. So like let's do 4x squared minus 3x. Okay, and I want to do the derivative of this. All right. So if you just use the subtraction rule, this says do the derivative of 4x squared minus the derivative of 3x. Okay, so sure, that's the subtraction rule. We can finish this problem. But the reason why it's not really its own rule is because this is actually the same thing, and this is how you should see subtraction. It sounds weird, but this is how you should start looking at subtraction. This is actually this, right? Subtraction is just addition of a negative. So really this is just the sum rule. This is just the sum rule. So just, you could think about it that way. Either way is fine. This seems like more work to think about things this way, but, thinking of subtraction as addition with a negative can be a useful way of viewing things. And then just for completion, right? Constant rule, the 4 comes out, 4, and then times 2x to the 1 power plus, and then I got a negative 3, constant I can bring out, times, and then x to the 1, we already saw the derivative of that, it's just 1. Boom. Which gives me 8x minus 3. Okay. So another nice one is the exponential. One of the nicest ones you could get. The derivative of e to the x is e to the x. Nope. This is not a typo. You're waiting for the video to skip to something else and I've erased things. No, this is not a typo. The derivative of e to the x is e to the x. That's it. Easiest one to remember. Just the same function again. So, I mean, I could do an example, I guess, right? There it is. Boom. Done. Not too bad. I just will make a few comments on some of these things. These rules are to be used very precisely. So I'll give you a couple examples of what I mean by that. But if you're going to use one of these rules, you must have the function you're working with, the quantity you're working with, look exactly like the rule says. So let me give you an example of bad usage. Bad example. Okay, here's a bad example. I have got e to the 2x. Now, you might look at this and be like, oh yeah, come on, that's pretty much e to the x, so I'll just write this. Woohoo! This is wrong. We need a different rule for this because this is not e to the x, it is e to the 2x, which is different. You're not actually that far off in your answer, but this is wrong. All right, so there you go. I mean, that's it. This is just going to be practice, 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 practice. Just practice as many of these as you can, being precise about using the rules. They must match exactly how they look here. All right. Pay attention to these conditions. This only works if f is differentiable. The sum rule only works if each of the functions separately are differentiable, where you're looking at them, so on and so forth. So that's it. Any questions, let me know, and I'll see you in the next video.